this almost last topic is called stability. And you may be asking, well, what is stability? Well, it's not immediately what you might think. Stability, there's two types of stability, and it's referred to as equilibrium stability. So, you've got unstable and stable. Now they are both two types of equilibriums, and I'm going to draw two examples. Now that is not a banana hanging off a fishing pole, and that is not a seesaw. That is a rock on a floor. Let's put a floor thing there. Yeah, rock on a floor and a basket on a hanger. Now if you push a basket, the weight is acting downwards vertically, and if you push it, it's going to swing, but then the weight of the object pulling it downwards is slowly going to slow it down, and it will eventually stop. However, for the rock on a plane, it's balanced very unstable, so if you push it, the table thing's going to fall off like that, not like just straight down. It's like sack gravity and went straight through the earth, cutting a massive hole, people in Japan die, etc. So basically all that happens is the table falls off and the rock moves away, and that's unstable because it doesn't return to its equilibrium position. That is the definition of the stable bit. So hopefully you've got that. And again, ask me any questions if you want to. So then we've got going to tilting and toppling. So tilting is raises up, just raising it up basically, and toppling is when it actually folds over. So let's say we've got a wardrobe. This should be the same height at the top, so this is H and W is the base, and assume we're applying a force at the top, then for the object to fall, F times H has to be larger than W times B over 2. So force, F is the force, H is the height of the wardrobe, the weight, oh sorry, just realised this is weight, B should be on, W is weight, B is on the bottom for base, and yeah, and then divide by 2 is, crazily enough, dividing by 2. So crazy, so crazy. Almost as crazy as the way I put my rubber down. So that equation is the main equation you need to know for tilting and toppling. We've already talked about being, if you watch my other videos, we've already talked about the slope thing, whereas mg is cos theta and mg is sin theta, but I'll just go over it again. So assuming we've got an inclined plane, and we're going to use this inclined plane for some other stability we're going to go on to in a minute. So this is theta, and say theta equals 30, and we've got, just sorry, trying to think, yeah, so we've got a block here, and we've got, right, there we go, so we've got a weight, mg. Now mg is the weight, and it always acts downwards, wherever it is, down to the centre of the earth. And now you've got one force acting that way, one force acting that way. And now the one that's acting perpendicular to the slope, as you can see there, is at a right angle. And I'm not sure, I'm just going to come to the camera so if I can see that on the screen before I go back and have to edit it. Don't know if you can quite see that. Oh, good. Just gonna, I'll zoom it out, but I just want to keep it on that bit there. So hopefully you might see a massive head walk through. Yes, you do. So let's label that 30. So hopefully you can see that, can you? You might see my head. So that's 30. So that's the same angle, yeah, as that. So we've got the hypotenuse and the adjacent. And then for hypotenuse and adjacent we use cos. So that means this is mg cos theta. And this is the base, so that is the hypotenuse and opposite, which is the same. This is the same as that, so going down the slope is mg sine theta. Hopefully that's explained it to you a little bit. If you don't get that, of course, just send me a link and we will go through that one together. God's sake. Right, done. Right. So that's a little bit of stability, and you can continue with the rest of the course. So, with stability, the main thing to consider is, so I'll draw that slope again, and we've got a car, except with this car I'm just going to draw a triangle. So imagine this car is a triangle. Well, actually, so the centre of mass is at the top of this line, okay, don't know if you can quite see that, it's at the top of the line, and the base is there. So it's got a height of 1.8 metres. No. Wait a bit. Yeah, it's got a height 0.9. No, wait. 1.8. Over 0.9. Yeah, hopefully that's right. And theta there, theta there. Now them two thetas are the difference between like the wheel and the middle of the wheel, sorry, and then the angle of the slope. Don't know if me doing that's probably not helping, but anyway, listen. So we want to work out this angle between 90 degrees, so when it falls over. Oh, so what we need to do is work out this angle here. So we're using trigonometry. Half of 0.9 is 0.45. So if we draw it into a triangle, we can use either triangle. We can use a right one that's right angled. So it's 0.45 along the bottom and 1.8 along the top, and we want to work out that. Now tan is, if you use soccer tower, so sock ka tower, it's T is away, so it's opposite over adjacent, so opposite 1.8 over 0.45. I think that's right. Yeah, we're going to inverse tan that. Sorry, you may have to check it. I'm only saying that because I've just created this question now and it might not work. 1.8 over 0.45, and then that will give you, I'm just going to call it tan theta. No, I'll call it theta. Yeah. So that gets you that angle there, theta. However, that is not the final answer. What you need to do, because we want the angle other bit towards 90 degrees as the maximum toppling angle, because that's already the angle it's at. So 90 degrees minus theta equals topple, the maximum angle. Before the object will topple. As I said, hopefully that's got you understanding it, and good luck, we'll see you in the next one.